What's up guys, it's me, Sir Ernest, and today we're going to talk about how to calculate moment of inertia using the parallel axis theorem for any rigid object. From our previous videos, we derived the moments of inertia of certain objects that's rotated about an axis that passes through their centers of mass. Now, what if the axis of rotation is passing through not at the center of mass, but the axis of rotation would still be parallel to it? So for example, if we have a rigid object like this, and there is a well-defined moment of inertia that is rotated about its center of mass. Now let's say we allow this object to rotate about another axis of rotation. Let's say the distance of this point to the center of mass is r, and that is defined by this vector capital R. So if this is our new axis of rotation that is parallel to this axis of rotation about the center of mass, therefore, we can use the parallel axis theorem to calculate the center of mass in our new axis of rotation. To do this, let's derive the expression for the parallel axis theorem. So let's say we have a representative particle. Let's call that I, and the mass of this representative particle is Mi. The position of Mi can be expressed in terms of two reference points. One would be its position with respect to the axis of rotation, O. Let's call that Ri. And we define the position of this particle with respect to the center of mass, Ri prime. If this axis of rotation is at the origin, so let's say this would be your x and this will be your y. Therefore, the axis of rotation would be parallel to the z-axis. So this becomes Iz. Now, for this particle I, the moment of inertia is given by Izi equals Mi Ri squared. And this is also equal, and by Pythagorean theorem, this is equal to Mi times Xi squared plus Yi squared. So therefore, the total moment of inertia of this object would be equal to the sum of Mi times Xi squared plus Yi squared for all i's. So again, here Mi is the mass of particle I, and Xi and Yi are the positions of particle I with respect to the origin. So here from this relationship, we can express Xi and Yi as follows. Xi would be equal to Xcm plus Xi prime, while Yi would be Ycm plus Yi prime. Thus, the moment of inertia would be equal to sum of Mi times Xcm plus Xi prime squared plus Ycm plus Yi prime squared. And this is equal to the sum of Mi times Xcm squared plus 2 Xcm Xi prime plus Xi prime squared plus Ycm squared plus 2 Ycm Yi prime plus Yi prime squared. So grouping Xcm and Ycm together, Xi prime and Yi prime together, we can rewrite this as sum of Mi times Xcm squared plus Ycm squared plus sum of Mi times Xi squared plus Yi squared. This is for all i's. And then plus 2 Xcm times sum of Mi Xi prime for all I plus 2 Ycm times sum of Mi Yi prime for all I. By definition of center of mass, these two terms are zero. Hence, the moment of inertia Iz will now be equal to sum of Mi times r squared, where r is the distance between the origin and the center of mass, and that is equal to Xcm squared plus Ycm squared, then square root. This is for all I. And this term would be the moment of inertia of this object about its center of mass. So this becomes plus Icm. Here is the parallel axis theorem. So therefore, the moment of inertia about the z-axis is equal to capital M, where M is the total mass, r squared, where r is the distance of the center of mass from your origin, in this case our z-axis, our new axis of rotation, plus Icm. So let's have a simple illustration. If we can recall from our previous videos that the moment of inertia of a thin rod rotated about its center of mass is equal to 1 over 12 ma squared. Now, if we change the axis of rotation from the center of mass towards the end, like here, we can use the parallel axis theorem to calculate the new moment of inertia. So the new axis of rotation is a over 2 away from your center of mass. So using the parallel axis theorem, we can calculate the new moment of inertia as follows. So this is I equals m would be the total mass times r squared, where r is the distance between the center of mass and the new axis of rotation. So in this case, this is a over 2 squared plus the moment of inertia about the center of mass. So this is 1 over 12 m a squared. So we can calculate this as follows. So 1 half squared would be 1/4 plus 1/12 times m a squared. So this is 3 over 12 plus 1 over 12 m a squared. So this gives us the new moment of inertia to be 4 over 12 or 1/3 m a squared. And as you already know that this is indeed the moment of inertia of a thin rod rotated about an axis passing through one of its ends, which we already calculated before using the definition of moment of inertia for various rigid objects. And here, in this video, we demonstrated that we can arrive at the same thing using the parallel axis theorem. So that's it. That's a very brief introduction to parallel axis theorem. I hope you learned something today. Thank you for watching, and I'll see you guys in the next video. Bye-bye.